This video is about sigma and pi bonds. Before we can talk about those bonds, we need to talk about shapes of orbitals. So we know that based on the uncertainty principle that you can't know the exact position of electrons. However, we can create these probability pictures that show their likely positions. You can see in this diagram that the likely positions of electrons is represented by a dense region of dots. We could summarize these depictions using shapes. Let's break it down by looking at the different energy levels when looking at electron configuration. We'll start by looking at the 1s and 2s energy levels. Each of these have one orbital, and since there is only one orbital, they will form a spherical shape. Now, this next energy level, the 2p level, contains 3 orbitals and each orbital has equal energy. You can see here that they will form what we call a dumbbell shape, and we can represent each orbital as 2px, 2py, and 2pz. And this will help us understand how they sit next to each other in a 3D Cartesian plane. Now, if we were to look at this more closely, we could see that each of these orbitals sits perpendicular to the others. So that means the angle between each orbital is 90 degrees. So the question is, if orbitals are spherical or sitting at 90 degrees to each other, how do we end up with these strange VSEPR angles of, for instance, 109.5 degrees? Well, this is where valence bond theory comes into play. When a bond forms between two atomic orbitals, each with one electron, the orbitals overlap to form a new molecular orbital that has a lower energy. Let's have a look at an example between two s orbitals. The simplest one that we can look at is between two hydrogens to form the H2 molecule. So the electron configuration of hydrogen looks like this, where we've got one electron in the 1s orbital, and the shape, as we know, is spherical, with the valence electron sitting there ready to interact with something else. So if we take two of these and form one full complete orbital with two electrons, then the two spherical shapes actually need to overlap, and this forms a new molecular orbital. If we have a look at the energy of different orbitals when looking at electron configuration, you can see that the 1s orbital has the lowest energy all the way up to 3p in this diagram, but we know that it keeps going. And the molecular orbital that we've formed in the H2 molecule is at a lower energy. And this means that it's more difficult to remove the electrons from this H2 molecule than it was to remove an electron from the 1s orbital. Okay, let's look at another example between between n, s, and p orbital. And we're going to look at the HF bond. So the electron configuration for hydrogen is the same as above. Electron configuration for fluorine, we can see that one of the orbitals in the 2p energy level is only half filled, so needs to join with another orbital to have a complete orbital. And I'm going to label them as 2pz, 2px, and 2py. And it is the 2py orbital that we're interested in. And you can see that along the same axis here, that the bell-shaped orbital of the fluorine, 2py, merges with the spherical orbital of the hydrogen to form this new molecular orbital with the electrons contained. A third example, we have 2p orbitals, and I have specified that these will be end-on, and that's because there are other ways that two p orbitals can bond. So if we take two fluorine atoms with the same electron configuration mentioned previously and line them up next to each other, again, I'm going to look at 2py as the incomplete orbital. And you can see that in the middle here, we've got the overlap occurring and a new molecular orbital forming. All of these examples we've looked at are bonds called sigma bonds, and these are represented with the Greek letter for sigma. Sigma bonds are covalent bonds that occur when an end-to-end overlap of two orbitals occurs. You can sort of think of this as the overlap occurring between two orbitals on the same axis, like this example here. All single covalent bonds are sigma bonds. So what does that mean for double or triple bonds? Well, let's have a look at the p energy level and its associated orbitals again here. And we can see that if we have the orbitals lined up on the same axis, then the sigma bond can form. But now that we have these orbitals lined up, the other orbitals are not able to line up so that they're sitting on the same axis. However, they can still form a bond. They're going to need to bend over and sort of bond in a way that distributes the electrons differently. When two p orbitals overlap sideways, the electron density region is concentrated above and below the plane of the bond axis. And this is what we call a pi bond. Double covalent bonds contain one sigma bond and one pi bond, and triple covalent bonds contain one sigma bond and two pi bonds. And it is also worth noting that pi bonds are weaker than sigma bonds because their electron density is further from the positively charged nucleus, and this means that they are easier to break in chemical reactions. Now, I just put this image here to show you what these pi bonds look like. So if we look at these two orbitals here, so the one that's looking directly up and down around the central atom, if they were to bend over and form a pi bond, you can see the electron dense region is above the sigma bond and below the sigma bond. And so although it sort of looks like it's two separate bonds, this is in fact one pi bond. And it's similar for the second pi bond. We have a region above and below along that axis. So this example is a triple bond. And yeah, it's just worth noting that the pi bond has a region above and below, but it doesn't mean that that's two pi bonds. It's only one.